Modern global logistics networks operate in highly stochastic, partially observable environments. Millions of independent variables, from cargo ships to autonomous trucks, move simultaneously without perfect information about each other's current states. To manage this complexity, the industry relies on optimized centralization and rigid rules-based automation. A central server attempts to ingest all network telemetry, calculate the ideal path for every vehicle, and issue commands from the top down. This diagram shows the exact moment a centralized solver bottlenecks. These models require a stable data environment to function, but when variables like port closures or storms change in real time, the central hub cannot recalculate the entire global network fast enough to remain relevant. This top-down rigidity ignores the reality on the ground. Trucks and autonomous hubs are independent actors encountering localized disruptions that a distant central server cannot immediately parse or resolve. Global logistics has moved beyond the reach of predictable routing equations. It is a decentralized decision-making challenge that centralized models cannot physically scale to meet. Single-agent reinforcement learning is the standard algorithmic approach for navigating these types of uncertain environments. An agent observes its surroundings, takes an action, and learns a strategy based on the resulting mathematical reward. However, mathematical chaos ensues when multiple independent agents operate in the same logistic space. When Agent A calculates an optimal route, it assumes the environment is stable, even while Agent B is simultaneously changing that environment by taking its own actions. This creates non-stationarity. Agent A's optimal policy breaks because Agent B's learning changes the ground truth. Without coordination, the entire system is trapped in a continuous loop, unable to reach a stable Nash equilibrium. Solving this gridlock requires moving from isolated learning to a layered multi-agent reinforcement learning, or MARL, architecture. To scale AI to global supply chains, we must replace independent learning with a system designed to balance collective intelligence with localized execution. The architectural foundation for this is centralized training with decentralized execution, or CTDE. It solves the non-stationarity problem by separating the learning phase from the deployment phase. In this framework, agents train collectively inside a high-fidelity digital twin. This simulation provides global observability, allowing the central system to develop joint action policies, teaching each agent how its individual decisions impact the entire group. Once training is complete, these complex strategies are compressed into lightweight policy packets and pushed down to the edge agents. During execution, they operate independently, relying only on local observations without a central link. This eliminates the need for constant communication with a central command, bypassing the latency and bandwidth limits of live operations. CTDE ensures agents learn to collaborate globally, but retain the ability to act the moment they encounter a physical disruption. To maintain this coordination at scale, we must look inside the internal software architecture of the individual agent node. Layer 1 is perception. It parses raw environmental data into a structured format. Layer 2 is coordination, preparing that data for interaction with other agents. Layer 3 handles decision-making, executing reinforcement learning policies to choose the most efficient action. Layer 4 is optimization, refining reward signals to align with network goals. Modularizing these functions allows for targeted updates. Engineers can update the perception layer to support new sensors without retraining the agent's core logic. This separation of concerns allows for the insertion of safety constraints at each step, providing behavioral predictability required for enterprise deployment. A major constraint of decentralized systems is bandwidth. Thousands of agents cannot broadcast full sensor data in real time without overwhelming the network. Graph neural networks offer a solution by enabling scalable coordination through localized connections. This architecture utilizes message passing mechanisms. Rather than sending data to a central hub, agents communicate directly with their immediate neighbors. To keep the data load light, they only share bandwidth-efficient policy data and immediate intents. This allows information about a disruption to ripple through the network at low latency, letting agents route around problems without waiting for permission. Message passing turns isolated agents into a responsive ecosystem that maintains global coordination while staying within a strict bandwidth budget. However, the final risk is selfish optimization. where an agent maximizing its own speed causes a bottleneck for the rest of the fleet. To prevent this, the system uses value decomposition. The global reward for network efficiency is mathematically broken down and assigned to specific local actions. Reward shaping ensures an agent is only rewarded when actively contributing to the global state. By utilizing actor-critic methods and proximal policy optimization, the system can manage these rewards across complex continuous action spaces, like speed and steering. Value decomposition stabilizes the learning process, ensuring that decentralized agents work toward a common goal without the need for a central dictator. In a fully realized MARL network, the system responds instantly to disruptions. Nodes reroute and self-optimize locally, preventing cascading delays seen in traditional models. This CTDE architecture is deployed via cloud edge infrastructure and distributed data pipelines, allowing the heaviest calculations to stay in the cloud, while the execution stays at the edge. The system performs multi-objective optimization, balancing constraints across time, cost, energy usage, and carbon footprint simultaneously. Integrating these models with high-fidelity digital twins allow complex policies to be validated against realistic disruptions before a single physical vehicle is deployed. This shifts the supply chain from a fragile, centrally commanded entity into a resilient, self-optimizing ecosystem. From a governance perspective, the modularity of this architecture supports the transparency and regulatory compliance needed for enterprise use. Future research is now combining MARL with generative models and predictive digital twins to anticipate shocks before they ripple through the network. Modern global logistics cannot be managed as a fixed equation. Multi-agent reinforcement learning provides the coordination needed to scale autonomous supply chains in a world that refuses to be predictable.